And we will move to chapter 15. Kinematics. I hate this chapter, and I hope, and I will do my best so that you like this chapter. Kinematics of rigid bodies is a very difficult one. Later on, this understanding on kinematics of a rigid body will make you to understand all the kinematics related with complicated link that is normally used for complicated mechanical system. Okay, so that is a very essential part, but it is difficult. Let me first show you why it is difficult. Okay, from a systems of particle, we learned that external force unbalanced induce mass to move with the acceleration a. Or in other words, this actually comes from linear momentum, rate of change of linear momentum with respect to time for a system of particle. And we found that this is same as m bar, which is the total system, and ag. And also we found that all the internal force is zero, and there is no contribution on this formulation. Okay, that was given to you as a classroom homework. Okay, so if we draw the picture using the famous two-bar system which I brought in this class, okay, that says if I apply force F1 and the force F2, that has to be equal to, okay, here is the center of mass, equal to what the force equation says, that is equal to this plus that where m bar is equal to ma plus mb, where this is ma and this is mb. Okay, the first equation is essentially graphically drawn like that. Okay, no problem. Okay, what if I take a moment with respect to center of, with respect to, for example, this coordinate? Okay, that is what? That is moment with respect to g. Okay, right? That is moment with respect to g. If I use notation 0, that is the moment with respect to the point O. Maybe I can use the coordinate over here. Okay, this is, we found equivalent with hg angular momentum with respect to g, but measured the coordinate that is not moving. And also we were very happy to find that this is the same as hg prime is the angular momentum, change of angular momentum with respect to time, but measure the centroidal frame of reference. The only difference is here all the momentum has to be expressed like that, Ri and Vi. Ri is the, for example, this is R1 and this is R2 in this case. Okay? And Vi is equal to, that is the absolute velocity. Therefore, that is the velocity of Vg plus Vi prime. Vi prime is the velocity measured with respect to g, x, y. Oh, this is an expensive one, right? So velocity with respect to g of this rigid body is this rotational velocity, and the total velocity is the velocity of center of mass plus velocity of each tip measured with respect of center of mass. Right? Therefore, as you already anticipated, this business is looking at the rigid body velocity with respect to center of reference, centroidal frame of reference, or absolute coordinate. That business make us in the beginning very complicated. So let's study the business associated with this first. Okay, that's what chapter 15 is looking for. Okay, and don't worry. However, this attempt is very simple. Okay, recall first. This whole business is associated with this expression. The position vector RB, I mean, there is a certain position that expresses the position of B is equal to RA plus RAB. And this is the position that is measured with respect to A point. And that's easy. That's very straightforward. For instance, again, let's have this example. Okay. Next lecture, we will bring the famous bar again here. Okay. And if I select a coordinate over here, and this is RB vector, and this is RA vector. And simply say that RA vector is equal to RB vector plus RAB. That's graphically very straightforward. Wrong, huh? What? Okay. Okay, that is very important. Right. Okay, now. Okay, this is a rigid body, no longer particle. Very special case, let's look at. This one is, very general case is this, right? Very general. Center of mass is moving, and there is a rotation. And what is the simplest case? Simplest case is this, translation. And another simplest case, it moves like that, but still only translation. Okay? Then, the special case, let's see the special cases. First, translation. Translation means RBA is equal 0 always. Right? RBA is always 0 in this case. Okay, what about starting this? What about this case? There is a RBA because of what? Rotation. For the plane motion case, translation and rotation. So for pure translation, this is 0. And secondly, if there is only rotation, then RBA is not, of course, 0. It has to be expressed, something that has to do with rotation. Rotation. How to express rotation? Rotation. Rotation, right? It's an expensive one, right? Oh, rotation. And as you can see, this rotation and that rotation and this rotation, there are 3 different types of rotation. It's complicated. So highlight of this chapter is to study about the rotation. If you understand rotation solidly, then no problem. And my responsibility is to make you understand rotation. So let me continue.